The airspeed indicator is the primary instrument pilots look out to ensure their airplane remains within its structural safety limits. The dial embeds hard-coded operational boundaries. Stall speeds sit at the bottom of the scale, normal cruising speeds occupy the middle, and the never exceed red line marks the absolute maximum at the top. These specific operational zones are marked directly on the glass. The white arc shows the flap operating range, the green arc defines normal operations, and the yellow arc warns of caution. But while this gauge accurately measures forward velocity, reading it in isolation hides a second physical dimension acting on the airplane. Velocity alone does not tell you how much physical stress the airframe is enduring. A pilot maneuvering aggressively within the green arc can easily rip the wings off an otherwise healthy airplane. To understand the true limits of flight, we have to measure velocity against structural stress at the exact same time. That critical missing variable is load factor, commonly known as G-force, the gravitational load applied to the structure during a maneuver. If we take the curved color bands of the airspeed indicator and unroll them into a straight horizontal line, we form the x-axis for our indicated airspeed. Intersecting that is our vertical y-axis, representing load factor, measured in positive and negative g-forces. Plotting these two dimensions together creates the velocity load factor graph, or VG diagram. This map defines the absolute boundaries of an aircraft's physical survival. In straight and level flight, gravity acts on the airframe with exactly 1 g of downward force. This is the baseline static load factor. Aerodynamic maneuvering, like executing a steep 60-degree banked turn, physically multiplies this baseline force. Any abrupt change in direction concentrates this increased load, whether banking heavily or pulling out of a steep dive. This stress goes directly onto the wings. The Federal Aviation Administration sets strict structural certification boundaries for these forces, known as the limit load factor. For a standard, normal category light aircraft, the structure handles a maximum positive load of 3.8 Gs and a negative load of 1.52 Gs. We can plot these hard limits onto our graph as horizontal barriers above and below the baseline. Pushing an airframe past these horizontal lines risks permanent structural deformation. The airplane ceases to be a functional aerodynamic vehicle and becomes a failing physical object. To understand how velocity interacts with these strict limits, we turn to the low speed end of the indicated airspeed axis. At low velocities, an aircraft wing has a physical limitation in how much lift it can generate. This limitation appears on our diagram as a sweeping curve originating near zero and arching outward toward the structural limits. The region to the left of these curves represents an impossible state of flight, where the wing cannot produce enough lift. Consider what happens if a pilot violently pulls full aft on the control column while flying at a slow speed. The wing reaches its critical angle of attack almost instantly, stalling entirely before it can generate enough lift force to hit the upper structural limit.
At these low speeds, the aerodynamic stall acts as an automatic safety valve. The wing gives out before the metal does, protecting the airframe from structural failure. However, there is a specific mathematical threshold where this aerodynamic protection disappears. It exists right here, at the exact point where the curved stall line intersects the hard horizontal limit load factor line. In aviation, this precise coordinate is called maneuvering speed, or VA. The physics of flight change completely depending on which side of this vertical line you are operating. Above maneuvering speed, the wing is moving fast and operating at a very small angle of attack. If a pilot abruptly applies full control deflection here, the wings have an enormous reserve of lifting capacity. That excess lift instantly translates into extreme G-force. The load easily blows past the positive structural limit before the wing has a chance to reach its stalling angle. Maneuvering speed is the pivot point for survival. Below it, an aggressive input stalls the airplane. Above it, that exact same input bends the airframe. Moving to the high-speed right side of the diagram, the primary threat shifts from pilot input to environmental forces. We can cap our graph by plotting the upper limits from the airspeed indicator, VNO, the normal operating limit, and VNE, the never exceed speed. Even if a pilot makes no control inputs at all, the atmosphere contains invisible hazards in the form of turbulent air and strong thermal gusts. An abrupt, powerful upward gust can violently alter the direction of the local relative airflow rushing over the wing. This artificially and instantaneously increases the angle of attack, generating a massive, uncommanded spike in lift. At high cruising speeds, this instantaneous lift spike can slam the aircraft up through the structural limit load line in a fraction of a second. Flying fast through turbulence strips away a pilot's ability to control structural loads. That is why the normal operating limit is a strict boundary in anything but perfectly smooth air. This fully assembled diagram reveals the complete flight envelope, a bounded geometric shape where safe operation is physically possible. Venturing outside these plotted lines places catastrophic forces on the physical hardware of the airplane. When the limit load factor is intentionally or accidentally exceeded, the internal metal structure yields and breaks under the stress. Most modern light aircraft use semi-monocoque construction, meaning the structural load is shared between the internal framework and the outer aluminum skin. Consequently, even a non-fatal overstress leaves insidious, hidden damage. Rivets shear off beneath the paint, internal struts distort, and the metal skin subtly wrinkles. This is why any suspected structural overstress legally requires a complete inspection by a certified aviation maintenance technician before the plane can fly again. The limits printed on an airspeed indicator are not mere suggestions. The flight envelope is an unforgiving mathematical boundary that dictates whether the airframe survives the flight.